Good morning, everyone. My name is Pierluigi Cerulo, and I am an assistant professor at the University of Concepcion. Today, I'm going to speak about the morphological transformation of galaxies as a function of the environment, a redshift to between 0.2 and 0.9. I would like to thank the organizers of this conference for giving me the opportunity to speak and present the results that I've obtained so far on this project. Here you can see an outline of the talk. So I'll start by giving a brief introduction on galaxy morphology. I'll present the scientific problem and give a brief description of the data. Then I'll show the results that we've obtained so far, which I'll summarize at the end, giving a brief overview of the plans that we have for the future. I would like to stress that the results that I'm going to present here have been obtained in collaboration with the people that you see in this slide. The morphology is a qualitative way of characterizing the structure of galaxies. So basically, we look at an image and see whether a galaxy is more elliptical or more spiral-like. So traditionally, galaxies have been subdivided into ellipticals, lenticular or A0, spirals that are maybe unbarred or barred, and irregular galaxies. The morphology depends on the environment in which galaxies reside. And if you see the plot on the left-hand side of the slide, where you see the morphological fraction on the y-axis plotted as a function of the local density of the environment, you can see that the fraction of elliptical and lenticular galaxies increases with galaxy density, whereas the fraction of spiral galaxies decreases. And this trend, which is called as the morphology, which is known as the morphology density relation, is observed up to at least redshift of 1.5 in clusters. However, morphology is not the only thing that changes with the environment. If you observe the fraction of quenched or quiescent galaxies as a function of the environment, you can also see that it increases with galaxy densities. So star formation quenching and formation of early type galaxies are somehow connected. The problem is how they are connected, which is what we try to address in this work, especially the links between star formation quenching and morphological transformations and how the environment affects all this. We are using a sample of cluster and field galaxies that we drew from the Clash and Kendall survey. Since this is an ESO conference, I would like to stress that Clash and Kendall are both surveys that have been carried out with the Hubble Space Telescope. However, the spectroscopic follow-ups have been conducted with ESO, at ESO, and especially with VMOS, and particularly with VMOS. So I can mention the Z-Cosmos and Legacy surveys, and for Clash, the Clash VLT survey. Well, for both surveys, morphology is available. Kendall's, the morphology in Kendall's was published with Huerta's company till 2015. And in Clash, we did the morphology and published it in 2019. You can download the catalog at the link that you see in the slide. The peculiarity that this catalog has is that we determined morphology in all the 16 HST photometric bands. So morphology is available from the near ultraviolet down to the near infrared. What we did to study the links between quenching and morphological transformation or formation of early type galaxies as a function of the environments was to take galaxies in Clash and galaxies in Kendalls, split them into star forming and quiescent using the UVJ diagram, and split them further into low redshift systems and high redshift systems within the range 0.2 to 0.9, which is, by the way, the range of Clash. As a boundary between the low redshift and high redshift subsamples, we use the median redshift of the Clash clusters, which is 0.45. And so in this plot, you see on the left-hand side star-forming galaxies, and on the right-hand side, quiescent galaxies. At the bottom, the low redshift subsample, and at the top, the high redshift subsample. Each plot shows the fraction of morphological types as a function of the stellar mass of the galaxies. Red symbols are elliptical galaxies. Green symbols are what we call the early type disks, which are galaxies that have a bulge and a disk, a significant bulge and a disk component, so like zero and SA galaxies. And then the blue symbols are all whatever is disk dominated late type galaxies, and late type spirals and irregulars. The shaded symbols are the field galaxies, and the field symbols are cluster galaxies. Unfortunately, for star-forming galaxies, we could only gather a small sample of cluster systems. So it's less than 100 in each of the high and low redshift subsamples. So you can see that there is a mixture of morphological types in clusters, whereas in the field, the star-forming galaxies are mostly late types. But we cannot draw any statistically robust conclusion, because star-forming galaxies, the star-forming samples, the cluster star-forming sample that we managed to build was too small. So let's focus on the right-hand side of the plot, the quiescent galaxies. There are two things that you can see here. If you go from high to low redshift, you can see that there is an increase at low stellar masses between 10 to the 9.5 solar masses and 10 to the 10.5 solar masses in the fraction of early type disks. And this happens in both cluster and the field. So in both the clusters and the field, there is an increase of quenched early type disks. Now, this is one thing. The other thing is that the trends of the morphological fractions with stellar mass in clusters are basically indistinguishable from the field. And this is quite interesting, because the quenched fraction in clusters is about twice than the quenched fraction in the field. Now, why is that? The problem is that when doing morphological studies, and this is where we are now, there are several things to consider before doing any physical interpretation. And one is that morphology is done in a passband. So here you see morphologies in the F160 band of the HST, near infrared. And near infrared is sensitive to all stellar populations, so bulge stars, basically. In Clash, we have morphologies in 16 bands, so we redid the plot for Clash galaxies in the F814 band, so it's roughly the I band. And and you can see that the high redshifts, there is a slight increase in the fraction of low early type disks, low mass early type disks in the high redshift subsample, which, however, the increase in the fraction of these early type disks remains, also if we observe morphology in a bluer band. The second thing that one has to consider, which is more severe than the effect of the passband, is the surface brightness dimming. And this is what we are currently doing. We're taking galaxies in the low redshift subsample in Clash, and are simulating them as we we're observing them at higher redshifts.
5 minutes
So
to
the idea
Q&A.
is, okay. So the idea is to redo the morphology on these high redshift simulated galaxies and see how many early type disks we simulate as ellipticals, because the disk fades below the sky level at high redshifts. So in summary, we compare, we study the morphologies in clusters and field galaxies redshift between 0.2 and 0.9, and find that the trends of morphological fractions with stellar mass are not significantly different between cluster and field. We find in both clusters and field an increase towards low redshift, about 20% of early type disks, of early type quiescent disks. We are currently testing biases, the biases induced by the surface brightness dimming, and we plan to go further with our analysis, looking at morphology in a more quantitative way through bulge disk decomposition. And then after we assess all the effect of the biases, of this surface brightness bias, we plan to compare our results with the predictions of numerical simulations. And of course, we want to extend our redshift baseline. So thank you for your attention, and I'll take questions and comments if you have. Thank you.